Oh my God. Now we are moving to theorem number 3. Now we're moving to theorem number 3, right? So now, this is how theorem number 3 looks like, and it's converse. You are given the circle, and have a look. These shapes are different, right? So now we have a triangle inside of the circle, triangle ABC, right? What do we know about this? Now, the theorem states that the angle subtended at the circle by a diameter. You see, now we are just saying diameter. We're just saying, we know these words. We started with the terminologies. That's why I wanted you to learn this thing so that you can understand what is a diameter. Line that passes through a center. All right. The angle subtended at the circle by a diameter is a right angle. We say that the angle in a semicircle is 90 degrees. In the diagram, that means angle C is equals to 90 degrees. This is straightforward. You don't even have to prove this one. This one is not the one that we're going to prove. The only thing that you need to know is that where is diameter? You have length. This is diameter A to B. This line AB, it is called the diameter. Diameter, it is subtending this angle over here. Look, in this triangle, we have chord this diameter, it's subtending this angle over here. But this angle over here, okay, let me do this so that you can understand, because already it's 90. I don't want you to understand it like that. So let's say we have a diameter, and then you have the center of the circle, and then the diameter is AB. And then we have chord who? Chord AC. We have chord CB, and then it happens they make a triangle. So now look, here's your diameter. This diameter, it subtends which angle? It subtends this angle over here, which is called the ACB. A angle CB, right? So A angle CB, because it is subtended by a diameter, what does that mean? That means if this is we're going to call that angle to be equals to 90 degrees. That means this angle will be 90 degrees because it is subtended by a diameter. So if you don't want to use that angle, if you don't want to use that reason, I get it, you're going to say, they're going to ask you, this is what they do in exam, or if they task you, obvious, using the theorem. Ne? They say to you, they just give you, they say this angle over there, it's x. And they say to you, determine the magnitude of x. You're going to say x is equals to 90 degrees. But remember, in Euclidean geometry, when you give the statement, you're supposed to give the reason. Why do you say x is equals to 90 degrees? We are applying the theorem to solve the problem. You understand? The problem is we don't know what is the magnitude of this angle. We just know that it is x. And they say to you, solve for x. You're going to say x is equals to 90 degrees. Then why? Because you're applying theorem number 1 and theorem number 3. You know that here you have a diameter. You're not supposed to be told. You can see diameter because it's passing through the center. You understand? So that means you're going to say x is equals to 90 degrees. Reason is you can use this angle. You can say angle subtended by a diameter. Or you can just use the simple reason that I love using. You can say angle in semicircle. So that's why we say x is equal to 90 degrees. You can also say angle in semicircle. That's why here they say, we say that the angle in a semicircle is 90 degrees. You can say x equals to 90 degrees. The reason will be angle in a semicircle. You are done. But you will see when you solve the questions. Just right now, I want you to remember these theorems and how they work. Okay? And therefore, this is the converse of theorem number 3. What is the converse? Remember, I said the converse, it is the reverse. Sometimes you're going to be provided with the circle like this, and then you have AB. We have AB, and let's say we have a triangle. And it happens that here we have 90 degrees. Ne? And they say to you, is AB a diameter or not? Remember, you can't say AB's diameter. Honestly speaking, you can't say AB's diameter without proving. Remember, you don't assume. Number one, you're not even given the center. So you can't say AB's diameter. But the only thing that can help you to say AB is diameter is what? You're going to use the reverse of theorem number 3. You're going to use the converse of theorem number 3. So what are you going to say? If you are given that angle C, it is 90 degrees, that means AB, it will be a diameter, because we know that if we have a 90 degrees here, only diameter can subtend that angle, which is the angle at the circumference. Ne? So that means if you are given that angle C is 90 degrees, therefore AB is a diameter. AB is a diameter. If you are told that C is 90 degrees, simple. That's the converse. Okay. I hope that was clear. Now let's jump to theorem number 4. Again, theorem number 4. Apparently we use theorem 4 to prove theorem number.
Can you please
Okay, come again.
Can you please repeat? Didn't hear you.
Sorry, come again.
Can you please repeat?
Theorem
Theorem number 3.
3. Okay. So I'm saying theorem number 3, it's easy. What does theorem say? If you are given circle like this, what is given here? Okay, let me do this. Theorem, let me do this. This is the circle, right? You have the center. You have a triangle like this. Ah, man, look at my drawing now. Let me do this quick. You have this. Okay, I know what to do. But that will waste my time. What I want to do will waste my time to draw a proper circles and stuff. Let me try it here. We have the circle. We have the center of the circle. And then we have the diameter. Okay, we have this. We have that. We have that. Ne? Again, let me draw another circle. We have the circle. Here we just have a line. We have this. And then we have that. Ne? So this will be theorem number 1. Number 3. This will be the converse of theorem number 3. So here, what is given? Here you will be given that, let me say A, B, C. A, B, C. Now here, theorem number 1 states that you are given that O is the center, right? You are given that O is the center. If O is the center, what does that mean? That means AB is the diameter. Or you are given that AB is the diameter. You can even be told that AB it is a diameter. Or you can be given the center. If you're given the center, we can tell that this is the diameter. You don't even have to be told that AB is a diameter. Ne? That's the first thing. So we are given that AB, or you are given the center, it is still fine. We are given that AB is the diameter. That's what it is given. Will come here. But here, what is given? Here in the converse of the theorem, we are given that here we have 90 degrees. Angle C is equals to 90 degrees. So this is the converse. Let's start with the theorem here. Let me change my color. So look, here, if you are told that AB is diameter, what does that mean? That means angle C is equals to 90 degrees. Simple. That means angle C is equals to 90 degrees. Why? Because what we know according to the theorem is that when we have a diameter over here, this diameter will subtend, the angle that the diameter will subtend, it will be 90 degrees. So you're gonna say, you can use the reason that it's semicircle. We say C is 90 because C, it is in semicircle. That's theorem number 3. The converse does the same thing, but the converse is you are given the opposite of what you're giving initially. The converse says that if you are told that here is a 90 degrees, therefore, remember, this is not a diameter because we don't have a center, and we can't assume that this is a diameter, but we need to prove here at least that AB, it is a diameter. So how are we going to prove that? We're gonna say that AB is a diameter. You just write that. Why? Because look, AB subtends 90 degrees. This angle over here, look, if the angle subtended by a chord, I get it's a chord right now, it's not a diameter, it's a chord because it doesn't pass through the center. We don't see the center. So if the angle subtended by a chord at a point of the circle is 90 degrees, like here, this is 90 degrees, then this chord, it is now called the diameter. Simple as that. Do you get it now? Hello?
Yeah, I get it.
All right. Thank you. Remember, you can take your screenshot, right? If you wanna, I don't know, if you wanna take your notes, you can screenshot for now, and therefore, because I'm gonna have to erase. Right. Now we move to theorem number 1, 2, 3, 4. We move to theorem number 4. So theorem number 4, it says to us, an arc or line segment of a circle subtends equal, an arc or line segment of a circle subtends equal angles at the circumference of the circle. We say that the angles in the same segment, you know what is a segment by now. We say that the angles in the same segment of the circle are equal. So what does that actually mean? It's simple. So that means angle A will be equals to angle B, angle C equals to angle D. We have the circle, right? Me explaining, I'm actually explaining this, né? You can just read it at your own time to make sure that you understand it better. So we have the circle once more again. Look at this circle. Look at this circle. We have angle theta is equals to angle theta. We have, I'll say dot or what? Yeah, I'll say dot. I'll call it dot. We have angle dot. We have angle dot. They are equal. But why is this the truth? It's because of this theorem, né? So we say, what's the reason? Why do we say angle A is equals to angle B? We can see that angle A is equals to angle B, which means dot is equals to dot. Why do we say angle A is equals to angle A? Because we are talking about the angles that are in the same segment. Ne? You know what is a segment. I told you what is the segment. If you don't use that angles, we can say that the angles in the same segment of the circle are equal. That's the reason that you give all the times, and I know you know that. But if you want to understand that, or you can say the angle subtended by the same arc. If that were, which arc? This is the arc that I'm talking about. Look at the arc, look at the arc AB, look at the arc AB, subtend this angle and that angle. Or look at the arc DC, subtend this angle and that angle. So these angles, because they are subtended by the arc, they're going to be equal. If you had a chord, you can also use that reason. Angle subtended by the same chord or angle subtended by the same arc. Or the third reason that you can use is angles in the same segment. That's the reason that I love using. Yeah? These angles, they are equal because they're in the same segment. We use that reason. It's easy. You don't have to complicate your life thinking hard or wanting to do something. This is theorem number 4. It states that. Okay? It says that if you have a butterfly, I love calling it a butterfly. Let me draw my circle. And then I have my butterfly. There is my butterfly. Let me draw my butterfly. There is my butterfly. Can you see my butterfly? And be careful. The vertices or the corners of your butterflies, they're supposed to touch the circumference. Look, it's touching the circumference, meaning the circumference is the circle, right? It is touching the circumference this side. It is touching the circumference this side. It is touching the circumference this side. So this butterfly is supposed to touch the circumference to talk about theorem number 4. Now look, let me call this angle angle A and this one angle B. This angle and this angle, they are going to be equal. So that means angle A will be equals to angle B. Simple. Why? Because these are the angles These are the angles in the same segment. You just write the segment, okay? It's a short for segment. Angles in the same segment. That's why we say this angle is equals to that angle. It's theorem number 4. It states this. It states that this angle are going to be equal if they're in the same segment, or this angle are going to be equal if they are subtended by the same arc. Or if we had a chord over here, this chord will subtend these two, or you can have chord that side, this chord will subtend these two angles. Ne? So that's the reason that we use, but I love using angles in the same segment to simplify life. We don't want complicated things for unnecessary things. So that's how we talk about theorem number 4. Now we move to theorem number 5. This is theorem number 5, okay? I'm sure you taking notes. How many theorems now you know? You know 1, 2, 3, 4. Now this is theorem number 5. Now, theorem number 5, it says to us, look, we are given the circle. Let me erase everything. This is theorem number 5. We are given the circle, right? So let us read the theorem. What does this theorem state? It says the opposite angles of a cyclic quadrilateral are supplementary, meaning they add to 180 degrees. So now this is what is happening. If you have a circle, just like this, and then you have a quadrilateral inside of the circle. I don't care how does this quadrilateral looks like. Ah, man. I really do not care how does the quadrilateral actually look like. But what I care about is, let me try this again. It really does not matter how your quadrilateral actually look like. Ne? Say we have this, 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 and that. I tried shape like this. Ne? So if you have a quadrilateral, what is the quadrilateral? It is a four-sided figure. Make sure, make sure that we are talking about one circle, right? Make sure that the vertices or the corners of your four-sided figure are at the circumference of the circle. If the corners are at the circumference of the circle, we call this quadrilateral. It is no longer just a quadrilateral. It is now called the cyclic quadrilateral. You know why we call it cyclic quadrilateral? Because it is inside of the circle and the vertices, like circle, cyclic. Quadrilateral, quad meaning quad inside of the circle. If you have something like this is not a cyclic quadrilateral. It is not. No matter how much you like it, this is not a cyclic quadrilateral. I understand 1, 2, 3, 4. It is a four-sided figure. This is a quadrilateral, not a cyclic quadrilateral. Why? Because look at the vertices are not at the circumference. Here I tried shape. Here the vertices, okay, only maybe this one it is at the circumference. Look at this one. It is not at the circumference. It is not. It is not. Therefore, it is not the cyclic quadrilateral. Same applies to this. Be careful. You see this theorem, theorem number 4. You see this theorem. I said to you, the butterfly is supposed to be the circumference. I'm going to theorem number 2. Look at the theorem number 2. Theorem number 2, it also has a butterfly, but be careful. Theorem number 2, one vertex is at the center. I understand this is the circumference. We have the circumference. We have the circumference. But look at O. O, it is not at the circumference. So it is a butterfly. You can't say O1 is equals to C. No. O1 is twice C. Don't forget. It's theorem number 2 because angle at center is twice angle at the circumference. Ne? Look, this shape is the same as this shape, kind of. It's giving butterfly. But this butterfly, look, circumference, 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 circumference. Everything is at the circumference. So be careful. So it's very important that you spot out your things are at the circumference. Okay? All right. Even if you have something like this, butterfly. I don't care. Look, I understand. This is at the circumference. You can't say this angle is equal to that angle. It will be wrong. Why? this thing is not even at the circumference. This thing is not it's not even second theorem. It's not even the theorem number 2. This is just the butterfly that does not even make sense. So be careful about these things, guys. Be extra careful about these things. I know when things are getting hard in exam, you'll be starting to make your own mathematics there, and you're gonna get them wrong. So be careful. So here on theorem number 5, this is how theorem number 5 works. Name, okay, it's a cyclic quadrilateral because the vertices are at the circumference. So theorem number 5 states that if you have a cyclic quadrilateral just like this, what does that mean? Let's call this A, B, C, D. You know what does this mean? What does this mean? It means that angle A plus angle C, they're gonna add up to 180 degrees. It's you just have to know it. You don't have to prove it. You will prove it later on. The only thing that you need to know, according to this theorem, it says that angle A plus angle C will be 180 degrees. But be careful, your angles supposed to be opposite to one another, meaning your angles are supposed to face each other. Angle A and angle C, they are opposite. They are facing each other. That's why we can just add them to 180 degrees. Only if this is a cyclic quad. This is true only if A, B, C, D, it is a cyclic quadrilateral. So that means also not only these two angles, which angles are opposite, which angles are facing each other. We can see that angle D as well, right? We can see that angle D as well. It is facing angle B. So that means also angle D plus angle B, they will add up to 180 degrees. Why? Because they're opposite to one another, and these are the interior angles of a cyclic quad. So the interior angles of the cyclic quad, they add up to 180 degrees. They are supplementary. Here we are talking about the converse of theorem number 5. Okay, this is the converse of theorem number 5, which says that if, but normally you don't use it most of the time, but it's fine. If the opposite angles of quadrilateral are supplementary, or in fact, this one, I need to show you, there is this thing, man, I need to show you, it's fine. So if the opposite angles of a quadrilateral are supplementary, then the quadrilateral is a cyclic quad. You know what's happening there? In exam, they say prove that this is cyclic quad. They love that question. I think grade 12s, they are familiar with that. Prove that this is a cyclic quad. Prove that this is a cyclic quad. This is the thing, né? This is the deal. I don't care whether the quadrilateral it is inside of the circle, it is not inside of the circle. I really do not care where is the quadrilateral at. But if you need to prove that this angle is a cyclic quadrilateral, let's say here, they give you that this angle is 80 degrees, and they give you that this angle over here, it is 90 degrees. 100 degrees, it's 100 degrees, ne? A, B, C, D. So if you add these two angles, how much are you going to get? And look, these angles are opposite to one another. So when you say angle A plus angle C, angle A, it is 80 degrees. Angle C, it is 100 degrees. When you add them together, we get 180 degrees. That means angle A plus angle C, they add up to 180 degrees. What does that mean? That means A, B, C, D, it is a cyclic quadrilateral, even though there is no circle. But the moment that you prove this is true, that means there is an imaginary circle that we don't even see over here. That means A, B, C, D, it is a cyclic quadrilateral. Whether this quadrilateral initially it was inside of the circle or it was not, or it was in a circle that doesn't even look like, or it was in a circle that looks like this. Look, this is not a cyclic quadrilateral. It's not, because look at the vertices are not at the circumference. But if it happens that here it's 80 degrees and then there it's 100 degrees and you add these two angles and they give you an 80, that means we have imaginary circle inside there. So that is this, it will be a cyclic quadrilateral. This is the first way on how to prove that a quad, it is a cyclic quad. So I want to hear what they did is we have this shape, and then it happened that these two angles, when we add them together, you will see how much you're going to get. You're going to say angle D, which is theta, plus angle B, which is 180 subtract theta. How much are you going to get? This theta will cancel that theta, and therefore you're going to left with 180. So that means when you add these two angles, you get 180 degrees. What does that mean? That means this thing, it is a cyclic quadrilateral. So that means it's going to look like this. You're going to have circle that's going to pass there. Just that you won't see it here, but obvious, using imagination, you're supposed to see something like this. The moment after you prove that this is 180, when you add them, you're supposed to see something like this in your head. And then remember, this is the converse of theorem number 5, because theorem number 5 says that if you have a cyclic quad, opposite angles, they add to 180. And the converse says, if the opposite angles, they add up to 180, therefore you have a cyclic quad. You understand what I'm saying? If you have a cyclic quad, the angles, they're going to add up to 180. Opposite angles, they're going to add up to 180. But if you have the angles that are opposite, that are adding to 180, that means you have a cyclic quad. It's the reverse. It is the converse. Right. So now moving on with the lesson. You see, I keep on emphasizing how does the converse work. Now, this will be theorem number 5. And there's the converse of 5. And therefore, now let's jump to theorem number 6. Theorem number 6, it is also on the quadrilaterals as well. So now, theorem number 6, it says to us, an exterior angle of a cyclic quad is equals to the interior opposite angle of a cyclic quad. It's like that theorem, yeah, triangle. This angle is equals to sum of these two. It's like kind of that thing, né? But it's not. It's just giving you heads up. All right, theorem number 6. So now, theorem number 6, look, we have a cyclic quad. How do you see like this is a cyclic quad? Remember, we have the circle. Look at the vertices, circumference, 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 circumference. Therefore, it's a cyclic quad. But now this cyclic quad instead, it is now different from this because now we have the angle, we have the exterior angle. Now this exterior angle, it is called angle C1. We can see that this is angle C1. So angle C1, it is actually going to be equals to angle A, which is this angle over there. Again, this theorem, it states that when you have the angle, the opposite, look, I get this angle is opposite to that angle. Remember, angle A plus angle C, they add up to 180 degrees because it's the opposite angles of a cyclic quadrilateral, right? Obvious, if you want to determine C1, you're going to use this angle plus 180 angles on a straight line. Same applies. You can say, oh, that means angle C1, it is the same as A. Okay? Angle C1, it is the same, angle A, it is the same as angle C1. And then the reason will be opposite, exterior opposite angle, exterior opposite angle of a cyclic quad. Opposite exterior, it's exterior because it's outside, is equals to opposite interior angle. This is the reason that we're going to give why we say C1 is equals to A. Okay, so now look, under theorem number 6, we also have the theorem converse, the converse of theorem number 6. Guys, when they say to you, prove that this is a cyclic quadrilateral, what I'm doing right now, you use the converse to prove that they love. What I had, this converse is very important. It's more than important than the converses that we did because they love these questions in exam. Grade 11, grade 12, they love these exams, these questions. I don't think you're going to have a question paper entire for the rest of your life without them asking you this question. So now look, the converse says, remember here, what was given? Theorem number 6, we were given that we have a cyclic quad. If you have a cyclic quad, that means exterior will equal to opposite interior. But here, we are not given that this is a cyclic quad. We just given that, oh, angle C1 is equals to angle A. If angle C1 is equals to A, and then we look at this diagram, this is a cyclic quadrilateral. Let's have a look at it. It's not just a cyclic. It is not just, it is a quadrilateral. But are we safe to say this is a cyclic quadrilateral? Let's see. Yeah, we can see that C1 is equals to A. This opposite exterior angle is equals to that opposite interior angle. Therefore, we are safe to say this is a cyclic quadrilateral. We assume or we visualize that the cycle passes at the circumference of the shape, which is this over here.